Hello, my name is Alfie Keary and I work for the Tyndall National Institute. I am presenting use case 3 from the IMOCO project called Tactile Robot Operations, and this is in conjunction with our partners Analog Devices. Before we actually go into the details on the IMOCO project, I think this is a very fitting and relevant paper called Tactile Robots as a Central Embodiment of the Tactile Internet. And specifically, it's an interesting slide because the graphic, as you can see, it presents, I suppose, what we foresee as the evolution of robotic teleoperations over the coming years, going from the very basic robotic arms right up to what the predictions are, robots working together to solve problems in the form of robotic collectives, so collaborating robotic collectives. Now, robotic teleoperation, I'd just like to mention that we see the future of soft collaborative robots interacting with people, and the ability for humans and robots to actually experience tactile sensations in terms of day-to-day operations. And of course, this will lead to the tactile internet, where you have such things as remote diagnostics is going to be very, very possible for touch and feel interactions, where there's all forms of different solutions that will become possible, and indeed work will become possible from multiple locations across the globe. So specifically, these developments would be framed in what we refer to as the Internet of Skills, and also another term is called the Internet of Robotic Things. So that is particularly positioning the whole use case 3 in the overall IMOCO project. And of course, other major advancements as to why we are going down this road of robotic teleoperation is addressing human safety. And we expect to see dramatic improvements in terms of humans interacting in dangerous, complex environments where you have got operational tasks to be completed, such as inspection and repair and decommissioning, when there's hazards and dangers involved for a human being. So that is a right and fitting introduction to use case 3 and its role in the IMOCO project. This graphic is, I suppose, a general overview. We don't have the time to go into detailed discussion, but what I'd like to point out is that in robotic teleoperation, there's going to be a operator user end, which is the local part of the platform. And then we also refer to where the sensors or actuators or robotic arms, robotic devices are being manipulated to carry out a specific task or action, which of course is all under the control of the robot, or is under the control of the user at the local end of the platform. This actually directly relates to the IMOCO project, and it's similar to the previous diagram, but it gives you an overview of the 4 layers. So our robotic teleoperation platform relates to all of the 4 layers of the IMOCO project. So specifically, you have the sensors, actuators down at layer 1. Then there is the intelligence and logic processing, condition monitoring, specific operational tasks and functionality, and particularly where the AI is embedded into the platform. So this would happen across layer 2 and layer 3 of our robotic teleoperation platform. And then as the platform advances up the TRL scale, we believe that a full-scale real-time digital twins module, which would be an integrated part of the platform. So the digital twin and AI analytics capabilities and reinforcement learning, machine learning, all of these type of activities would be part of the layer 4 of the IMOCO platform for use case 3. This gives you a more detailed breakdown It's not some of the thing that we will go into detail, but I just wanted to point out that using the 4 layers of the IMOCO project, you can see that there is various functionality defined down here in layer 1. A number of different forms of sensors have been tried and tested and interfaced with PC devices and also edge devices. So this is right down into the lower sensor layer. This I'm just presenting the local end. We have a similar diagram to represent the remote end of the IMOCO platform. Functionality here in terms of the robot movement processing, the data from various sensors are fed into layer 2. Then there is some form of AI analytics, predictive capabilities. All of this is built into the platform as well, and as already discussed, you have the digital twin and analytics layers of the platform. We see the digital twin specifically in our architecture existing at the local end, because that's where the user is going to be interacting and will need services from the digital twin layer. In terms of the IMOCO project, we particularly have addressed building block 1 in terms of edge devices. We have sensors, particularly vision sensors in building block 3, and also the AI components we've been working on under building block 8. We specifically have an interest in BB6, but considering the low level of TRL for use case 3, this would certainly be something for the future in terms of condition monitoring, predictive maintenance, in terms of a highly sophisticated robotic infrastructure. But that's why we've kept our interest and involvement in BB6. But primarily, use case 3 is BB1, BB3, and also BB8. This is a depiction of the hardware. I won't spend a great deal of time, but just to give you an overview that this is the edge devices. So we've been working with the Polar Fire and also the STM32 edge components. So clearly we are interfacing all forms of different sensors. So we have produced a tactile glove, a Tyndall, which we are working on to interface into our use case 3. We've been working with motion tracking sensors, and specifically we have put a lot of research with ADI into the time of flight. So processing of depth data in terms of being able to these time of flight camera technologies, being able to observe the user and communicate to the remote end exactly what the user wants to do. So these are the challenges, but clearly here at the local end you have all sensors connected onto edge devices. We do expect that some form of PC architecture will also be required. So you're looking at interfacing a certain amount of existing PC architecture with edge devices. So that's the focus for use case 3 at the local end, and we are using the Profinet industrial protocols in terms of communication from the local end to the remote end of the platform. Similar, you will see that we have edge devices in the remote end, and clearly here this is where the robots are. We are working particularly on the universal robot devices. We've worked on the UR16E at Tyndall, and also the UR5E is being used by Analog Devices and Indalo at their Catalyst lab, where complementary research is being conducted. So clearly here there is similar infrastructure, and all of this again is communicated across the Profinet industrial protocol in terms of interfacing between a local end and a remote end of our robotic teleoperations platform. The challenging areas today is how do we get all of this computing power onto edge components, because today they are still quite limited devices in terms of capability, but we certainly expect this to change over the coming years. So particularly what you're finding here is that the challenges of taking predefined models and optimizing these models onto these edge devices, and that's particularly some of the research work we're doing with our partners in Dalo, which is using the vector blocks technology to quantize and collaborate embedded AI onto the likes of the Polar Fire device and indeed other edge devices. So as a wrap up to our short introduction and overview of use case 3, we would see that the futures and challenges, very much so, one of our major problems is dealing with latency. So latency, the end-to-end latency between the local and remote end of the platform is one of the key challenges for use case 3. Also, sensors are continually advancing, so the capabilities to interface new and novel sensors into robotic teleoperations infrastructure, we believe, is a critical component of the development of the Internet of Skills and the Internet of Robotic Things. And that's clearly the challenges of human machine and collaboration and robot interfacing. Even though we have seen incredible uptake in terms of collaborative robotics over the last few years, there is still a great deal of work and technical challenges in truly having humans interacting together in performing day-to-day tasks, typically in a manufacturing environment. There's also the whole aspect of there's a lot of hype about AI and machine learning at the moment, and we feel that really that will cool down over the coming years and the real work will actually start. So we're at the very early stages of AI, and clearly we believe that the maturity of this field will fuel real potential and advancements in the whole area of robotic teleoperations. And of course as well, the true digital twins, even though there's a lot of interest and belief that digital twins in terms of creating virtual worlds of objects and experiences, the technology similar to AI is still at a very, very early stage. And particularly we see the integration and the merging of digital twin technology with advanced AI and machine learning to really create a highly sophisticated real-time world that through virtual reality a user could interact with and thus carry out real teleoperations activities from the local end of the platform. So that gives you a short overview of the use case 3 robotic teleoperations platform. And if you request further information, you have all of the contact information on the IMOCO website. Thank you very much for listening.